based theory. When you come for this automata based programming, it is a programming paradigm in which program or its parts is thought as a model of a finite state machine or any other formal automation. Okay, now when we come for automata theory, it is a study of abstract computational devices. Abstract devices are models of real computation. Computation happen everywhere in all aspects. Now we have a small example where we are lighting a bulb using a battery. Now when you go for lighting a bulb, we consider that we give the input through switches as on and off. So now the input is given through switches and we have on and off state. Now next, when you come for the output, it is lighting the bulb. It is lighting the bulb. So what is the action that you perform on the switches? You flip the switch to on and off. So the action that is performed is flipping switches, and the states that you come across is on and off. So this plays a very important role in automata theory, considering the input, output, action and states. So when you consider this example, the input is switch, output is lighting the bulb, the action is flipping the switch, and the states that you get are on and off. Next, when you come for this, we have given it in the form of a state diagram. The same example has been given in the state diagram where you have the start state. Initially it is in the off state. When you give a flip, it moves on to the on state. When you give another flip, it moves on to the off state. So what is that is, you can give your flips continuously where you get on and off. So when you see this flips, the action that has been performed, when it is odd number of flips, the bulb is in the on state. When it is even number of flips, the bulb is in the off state. So we can say that the bulb is on if and only if there was odd number of flips. Okay, again the same diagram has been given with an on state and 3 off states. It means that you have 2 switches. When you see the diagram, you can come across and check it out. You have 2 switches, 1 and 2. Action 1 for flip 1, and action 2 is for flip switch 2, and the states are on and off. So when it's in the on state, the bulb will start glowing. When it's in the off state, the bulb will remain off. Now we go for types of automata. When we go for types of automata, the first automata is finite automata, where devices with a finite amount of memory used to model small computers. When it is push down automata, devices with infinite memory that can be accessed in a restricted way. It is used to model parsers, etc. Turing machine, it is devices with infinite memory used to model any computer. Now when you come for alphabets and strings, now what is an alphabet? An alphabet is a set of symbols. So using these alphabets, we go for talking about words, numbers, pairs, but we go for representing the strings. Okay, so defines, when you want to go for the string, you have to know what is an alphabet. Now when you say what is an alphabet is a finite set of symbols. So we have given many examples. For example, a set of letters in English, set of base 10 digits, set of letters plus special symbols, set of open and closed braces. So all these are alphabets with a finite set of symbols. Now an alphabet over epsilon is a finite set of symbols in epsilon. So the empty string will be denoted by epsilon. Okay, now when you go for this strings, a string over alphabet is a finite sequence of symbols. So an empty string is denoted by epsilon. So when you give representation, you have given the examples has been listed out as same. Now language. What is a language? A language is a set of strings over an alphabet. So language is made on an alphabet. So it is a set of strings that you get from an alphabet. Languages can be used to define problems with yes or no answers. For example, L1, the set of all strings that contain substring SRM. The set of all strings that are divisible by 7. The set of all strings where S is any string over. The set of all strings where it has been matched with the subsequent strings. So you go for these types of examples. Next, finite automata. Now in finite automata there are states off and on. The automaton starts as off and try to reach the good state when it is on. So in the same way as we have discussed already, initially it is in the off state. When a single flip is given, it goes to the on state. Then when you give another flip, it goes to the off state. For first flip it is on, for second flip it is off. So when you give again a flip, it becomes on, and when you give again a flip, it becomes on. So when you consider a number as n, which indicates the number of flips, when n is odd, you have the bulb which has been enlightened as we discussed already, but here it is generalized as on. So when you have odd number of flips, when your n is odd, you will be in the on state. When you have even number of flips, when your n is even, you will be in the off state. So this is an example of deterministic finite automaton, where you can say clearly that when n is in the odd state, you will be in the on state. A deterministic finite automaton is composed of 5 tuples, where the first one is a finite set of states, second one is the alphabets, third one is the transition functions that we obtain, then fourth one is the initial state, and fifth one is the set of accepting states or the final state. So we have various symbols to define this. The first one is a finite set of states, second one is an alphabet, third one is the transition function that we come across, fourth one is the initial state, and fifth one is the accepting state or the final state. We have symbols to represent them. Now the next one is, we go for diagrammatic representation where the alphabets are 0 and 1. So you have two inputs which is 0 and 1. So whenever the input is 0, what will be the reaction? Whenever the input is 1, what will be the reaction has been given in the transition function. The inputs are 0 and 1 and the states are Q0, Q1, Q2. When Q0 takes 0 as input, it remains in the Q0 state. So it has been defined as like this. When Q0 takes 1, it takes the input as Q1. Now next, when Q1 takes the input 0, it is Q2. When Q1 takes the input 1, it is Q1. When Q2 takes the input 0, it is Q2. And when Q2 takes the input, it is Q2. So the last state that we come across, the accepting states are Q0 and Q1. So the initial state is Q0 and the final states are Q0 and Q1, and the different states that you have are Q0, Q1 and Q2. Next, language of a deterministic finite automata. The language of a deterministic finite automata, which has been represented in symbols, is a set of all strings. It is a set of all strings over the alphabets that has been given, which starts from Q0 and following the transition as the string is read left to right and will reach some accepting state. So which means that when you move from left to right, the string is read from left to right, which reach the accepting state. So when you have a flip from left to right, it is accepting state. So when you consider this, you have, when it is left to right, first will be left to right and then right to left, then it is left to right. So when you go across counting the flips, you can consider that when you come across odd number of flips, you will get this state. Next, you have certain examples to do with. Example of DFA using Python. So a DFA has been given which matches all binary strings ending with an odd number of ones. So you have a programmatic representation for this DFA. Then table representation of DFA. A diagram has been given. A DFA over A can be represented by transition T, states X, A to states, where T of I comma K is the state reached from I LO, the edge labeled as A, and we mark the state and final states from the example given. Now when you look upon this diagram, you come across the starting state is 0. The starting state is 0. Now the input that has been given is given in the edges. So when I move from 0 to 1, the input may be either A or B. It reaches the state 1. Now when you move from state 1, when the input is given as A, it moves to the state 2. When the input is given as B, it remains in the same state. Now when you look at the state 2, when input A is given, it remains in the same state, and when an input B is given, it also remains in the same state. So this representation has been given in the transition table. You have certain examples to go with for DFA. A non-deterministic finite automata. Now when you go for this non-deterministic finite automaton, again your M is a 5 tuple structure where the symbols are given for representation. Okay, now the first one is Q, which is a finite set of states of M. Then at the input element, finite input alphabet of M. Then it is a state transition function mapping a state symbol far to a subset of Q. Then Q naught is a state of M. Then F is a subset of Q, which is a set of accepting states or final states of M. Next, non-deterministic finite automata that recognize the languages of strings that ends in 0 and 1. So now I am going to construct a language that ends with 0 or 1. So my inputs are 0 and 1. So now when I consider Q naught, I am taking the input 0 and 1. When it takes the input 0, it moves to Q1 state. When it takes to its input as 1, it moves to Q2 state. Another possibility is when it takes the input as 0 also, it remains in the same state. When Q1 takes an input 0, it remains in the null state. Now, this is a representation of NFA that accepts all strings ending with 0 and 1. Now, we have a non-deterministic finite automaton over an alphabet A, which is similar to deterministic finite automaton except epsilon edges are allowed. There is no requirements to emit edges from a state and multiple edges with the same letter which can be emitted from the state. Now this is the representation of NFA that recognize the languages A plus A star B plus A star B. We have given a tabular representation of NFA for this to go with. Here we have the start symbol. Then we are going to find a non-deterministic finite automata to recognize the language A plus BA the whole star, B into A plus AB the whole star. So the solution has been given. Algorithm transforms a regular expression into a finite automaton. Start by placing the regular expression on the edge between the start and the final state. So when you look at the figure, you have start, then after the start it reaches a state, there a regular expression is given and it reaches the final state. Now we are going to apply rules to obtain a finite automaton after erasing epsilon edges, null edges. Okay, now I to J, where you go for getting inputs R plus and S, which transforms, and you have the diagrammatic representation of this. Now I to J, you take the input of R and S, where when I takes the input R, it moves to one state, from that input S to J. Next, when I to J R star, where I takes epsilon to go with, and when it takes R, it moves to J. So use this algorithm to construct a finite automaton for AB star plus BA. You have a diagrammatic representation for this. Then this has been we have an NFA which matches strings beginning with A, ending with A, and containing no consecutive B's. So you have the Python programming for this to represent. You have certain examples to go with. Symbolic